Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual history of physics contains moments of profound synthesis, instances where disparate domains of reality are unified through a single, powerful insight. Stephen Hawking's 1974 paper in the journal Nature, formerly titled Black Hole Explosions, represents one such moment of extraordinary convergence, while the popular imagination, and indeed Hawking's own later work, would expand its implications toward concepts like baby universes. The 1974 publication itself contains a more focused, and in many ways more disruptive, central claim. It presents the argument that black holes, are quintessential symbols of gravitational finality, are themselves active and finite objects that participate in the quantum life of the cosmos. This essay will undertake a rigorous, section-by-section evaluation of the internal claims, mechanisms, and physical arguments presented within that foundational paper. It aims to dissect the logic that joins general relativity, quantum field theory, and thermodynamics, revealing how Hawking constructed a paradigm that forever altered our understanding of gravity, information, and the ultimate fate of matter. We will proceed by examining the paper's logical structure, evaluating the coherence of its reasoning and the profound consequences of its conclusions, all while adhering to the specific framework of the work itself. Section 1: The Thermodynamic Challenge and the Rejection of Classical Absolutes. The paper commences by situating its argument within an ongoing debate concerning the thermodynamic properties of black holes. Its opening paragraphs establish the intellectual terrain by referencing the classical laws of black hole mechanics, particularly the area theorem, which states the surface area of a black hole's event horizon can only increase. This law bears a striking resemblance to the second law of thermodynamics, which posits the continual increase of entropy in a closed system. Hawking acknowledges Jacob Bekenstein's bold proposal to take this analogy literally, assigning a genuine entropy to a black hole proportional to its area. The initial claim, evaluated here, is Hawking's pivot from his earlier skepticism toward an embrace of Bekenstein's idea as a physical necessity. He frames the problem as a consequence of applying quantum mechanics to the situation. A black hole, by absorbing thermal radiation from its surroundings without possessing a temperature of its own, would appear to violate the second law for the universe as a whole. The paper's initial argument is thus a syllogism of refusal for thermodynamics to hold universally. Black holes must possess an intrinsic temperature and therefore must radiate. The evaluation of this opening claim reveals its strategic brilliance. Hawking reframes the problem from one of analogy to one of consistency. He accepts the premise that the established laws of physics are complete and then demonstrate that the classical conception of a black hole creates a fundamental contradiction. The methodology is one of logical reduction, forcing the reader to choose between abandoning universal thermodynamic principles or abandoning the classical image of a black hole as a perfect, one-way membrane. This setup is a masterclass in theoretical physics argumentation, clearing the ground for the introduction of a new physical mechanism by first demonstrating the untenability of the existing conceptual framework. Section 2: The quantum mechanism of particle emission at the event horizon. Having established the thermodynamic necessity of black hole radiation, the paper proceeds to its central physical claim: the specific quantum mechanical process that facilitates this emission. Hawking proposes a mechanism rooted in the principles of quantum field theory in imperfect spacetime. He describes the vacuum of space, understood in quantum terms, as a sea of continuously forming and annihilating virtual particle-to-particle pairs. In a flat spacetime of empty space, these pairs exist for fleeting moments before recombining, their existence constrained by the uncertainty principle. The core of Hawking's new physical argument lies in his analysis of this process near a black hole's event horizon. He claims the immense gravitational tidal forces in this region can separate a virtual pair. One particle, endowed with positive energy, can escape to infinity, becoming a real particle detectable to a distant observer. The other particle, to conserve energy, must carry negative energy as it crosses the event horizon and falls into the black hole. The evaluation of this claim delves into the heart of the paper's originality. The concept of negative energy particles, while counterintuitive, is a consistent feature of quantum field theory in certain contexts. By falling into the black hole, this negative energy particle effectively reduces the black hole's total mass energy. The mass lost by the black hole is precisely equal to the mass energy of the escaping particle. This mechanism is profoundly elegant. It provides a concrete physical picture for black hole mass loss while upholding the principle of energy conservation for the total system. The methodology here is a semi-classical approximation, treating the background spacetime as a fixed classical geometry described by general relativity, while the behavior of matter fields upon it is governed by quantum rules. This approximation is the source of the calculation's power and its limitations, a point Hawking himself understood. The claim's strength lies in its direct and calculable consequences, moving the discussion from abstract principles to a specific, albeit exotic, physical process. Section 3. The thermal nature of the radiation spectrum. The next logical step in Hawking's argument concerns the character of the emitted radiation. The paper claims that the stream of particles created by the quantum process at the horizon possesses a perfect thermal, or blackbody, spectrum. This means the radiation is indistinguishable from that which would be emitted by an ordinary hot object. The temperature of this spectrum, the paper asserts, is inversely proportional to the black hole's mass. This specific quantitative relationship is perhaps the most powerful claim in the paper. The formula for the Hawking temperature can be expressed in natural language as follows. The temperature is equal to the reduced Planck constant, a fundamental constant of quantum mechanics, multiplied by the speed of light cubed, with this entire product divided by the term 8 pi times the universal gravitational constant times the Boltzmann constant of thermodynamics times the mass of the black hole. An evaluation of this claim reveals its deep unifying power. By deriving a temperature from the first principles of general relativity and quantum mechanics, Hawking solidified the connection to thermodynamics. Bekenstein's entropy was now complemented by a genuine physical temperature, transforming the laws of black hole mechanics into true laws of thermodynamics. The methodology supporting this claim is a complex quantum field theoretic calculation, sketched in the Nature paper and elaborated in a more detailed publication that followed. The calculation shows that the quantum state of the emitted particles is a mixed thermal state. This result is profound. It implies that the emission process is statistical and random, lacking any information about the specific history of the black hole or the nature of the matter that collapsed to form it. The coherence of the argument here is remarkable. The derived temperature allows for the formulation of a consistent thermodynamic picture, validating the initial premise of the paper and providing a specific value that depends only on the fundamental constants of nature and black holes. Section 4. The astrophysical consequence of evaporation and terminal explosions. Building upon the previous claims, the paper concludes by exploring the ultimate physical consequence of this radiation process, the complete evaporation of the black hole. The inverse relationship between temperature and mass is the engine of this final act. As a black hole radiates, it loses mass. As its mass decreases, its temperature increases, causing it to radiate even faster. This feedback loop, the paper claims, leads to a runaway process. For astrophysical black holes with masses many times that of our Sun, this evaporation is an extraordinarily slow process, taking vastly longer than the current age of the universe. However, The paper makes a specific, testable prediction regarding hypothetical primordial black holes. These are small black holes, with masses perhaps comparable to a mountain, that could have been formed in the dense, turbulent conditions of the very early universe. A primordial black hole of a specific initial mass would be reaching the end of its life today. The final stage of its evaporation, Hawking claims, would be the violent burst of high-energy radiation, an explosion releasing a tremendous amount of energy in its final fraction of a second. An evaluation of this claim highlights its importance. As the paper's primary link to observational astronomy, it transformed a purely theoretical concept into a potential observable phenomenon. The search for the characteristic gamma-ray flashes from evaporating primordial black holes became a concrete avenue for experimental physics, a search that continues to this day. The logic of the claim is sound, flowing directly from the mass-temperature relation. However, the argument's own methodology reveals a crucial limitation. The semi-classical approximation used to derive the radiation breaks down in the final moments of evaporation. As the black hole's mass approaches the Planck mass and its gravitational field becomes subject to quantum fluctuations, a full description of the final explosive burst requires a complete theory of quantum gravity, a theory that remains elusive. Hawking's claim is thus both a brilliant prediction and a clear signpost pointing to the limits of current physical understanding. Section 5. The implicit challenge to quantum unitarity and the information paradox are final. Deep evaluation of the paper's claims reveals an implicit and perhaps unintended consequence that has shaped theoretical physics for half a century. The claim that the outgoing radiation is perfectly thermal carries a revolutionary hidden premise. Thermal radiation is characterized by its statistical nature. It contains almost no information, aside from its temperature. This implies that all the detailed, complex information about the matter that collapsed to form the black hole is ultimately destroyed during the evaporation process. For example, a star with a specific chemical composition and a library of encyclopedias could collapse to form a black hole, where the outgoing radiation would be identical to that from a black hole formed from a collapsing cloud of pure hydrogen, provided the final mass, charge, and angular momentum were the same. This outcome directly challenges a core tenet of quantum mechanics known as unitarity, which asserts that information in a closed quantum system is never truly lost. The creation of a pure, information-rich quantum state that evolves into a mixed, information-poor thermal state constitutes a fundamental violation of this principle. While the term information paradox was articulated more clearly in the years that followed, its seed is planted firmly within the 1974 paper's claim of a thermal spectrum. An evaluation of this implicit claim shows it to be the most contentious and enduring legacy of the work. It created a deep schism in physics, pitting the predictions of general relativity in curved spacetime against the foundational structure of quantum mechanics. Hawking's initial conclusion was that information was indeed lost, a radical departure from established quantum dogma. The internal logic of his semi-classical calculation led directly to this conclusion, exposing a profound incompatibility between the two great pillars of 20th century physics. This paradox, born from the claim of thermal radiation, has become a primary driver for research into quantum gravity, motivating new concepts like the holographic principle and fueling decades of debate, a debate in which Hawking himself would later play a central and ultimately revised conclusion in conclusion, a meticulous evaluation of the internal claims of Stephen Hawking's 1974 paper Black Hole Explosions affirms its status as a landmark of theoretical insight. The work's power derives from its tight, logical progression. It begins with a thermodynamic imperative, proposes a concrete quantum mechanism to satisfy it, derives a precise thermal character for the resulting emission, and follows this chain of reasoning to its ultimate astrophysical and theoretical consequences. The claim of quantum particle creation at the event horizon provides a stunningly elegant picture of black hole mass loss. The subsequent claim of a perfect thermal spectrum for this radiation successfully weds black hole mechanics to thermodynamics, yet it simultaneously gives rise to the profound information paradox that continues to challenge the foundations of physics. The final prediction of evaporating primordial black holes offered a tangible, though as yet unseen, observational signature. The paper's semi-classical methodology, while brilliantly effective, also clearly delineated the boundary where known physics must give way to a future theory of quantum gravity. The enduring significance of the 1974 work resides in its generative power. It resolved one set of problems concerning thermodynamics only to create a deeper set of questions concerning quantum information, by demonstrating that black holes are dynamic, finite participants in the cosmic drama. Hawking transformed them from mere gravitational endpoints into crucial theoretical laboratories for probing the unification of nature's most fundamental laws. The journey from this paper's rigorous claims to the more speculative realms of cosmic information and creation is a testament to the revolutionary potential contained within its few, carefully argued pages.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.